Hey everybody, how are we doing? We're giving out 100 extra credit points right here for Daniel wearing a suit right there. 100 points in the chat. Alyssa asking about the most points you can get. You can get up to a half point in your grade on the Discord, and you can get up to 1.2 points on your grade here by being in the chat. We're throwing out some crazy points. Be telling your friends if they're not here, be like, what are you doing? We're trying to get to those 50,000 points. Daniel getting more points there for the chat. So make sure to be here, be practicing, to be following along. We're nearing the end. We got our new music. Nearing the end of the class. Only a few more lectures to go. New material. I'm closing down like 1,000 web pages here. Closing all the web pages music going on right here on Stat 201. But how's everyone doing today? Good to see you, Daniel, Lissel. We got here Walker. We got here Reed, Nathan. How's everyone doing today? Last full week of school. Haslam Friday. I can't believe it. It just flew by. What does it say? Do you know where when we put out? I think last week. I'm fine with that. When the due dates are. Everyone's having a conversation right here. Oh no, it's missing. Oh, have we put up activity? I need that third cup of coffee today. Who's with me on third cup of coffee for the day? Can I get some third cup of coffee in the chat right now? Who wants that third cup of coffee? Because I know I do. Let's go look at... You know what? File not ready yet. Wait, what? Says Alan. We'll be opening up the take-home here pretty soon, Alyssa. Thank you for asking about that. Third cup of Diet Coke in the chat right there. Megan actually put some third cup of coffee. We'll have the take-home coming up this weekend right here, so get ready for the take-home. Lots of great stuff appearing, and looks like we will have the final activity getting posted here soon. What should we talk about today? Because I think we're nearing the end. We got some review coming up, 2 more classes after this. But we've been talking about logistic regression. And let's go into a little bit. I wish we could play It's the Final Countdown, Megan. I wish we could. It's the final countdown. We can't. Third cup kind of day. That's what I'm feeling right there. Third cup kind of day. And the third, the fourth, and the fifth cup of coffee. Yeah, for Brian. If Brian drinks those, he's going to be overloaded on his coffee. I'll have way too much coffee in me then. Let's start talking about this right here. Last time we finished off logistic. Let's just jump into it, everybody. Let's take the final in class today all together. Any advice for continuing in BAS classes? Oh, great question. Let's talk about that really quickly right here. Okay, so let's talk about some advice. Let me close down these files. Oh, sure, I saved that. Here's Brian's advice for continuing on in BAS classes. Let's go look at this. So the number one thing you could do over winter break is what? What do you think you could do over winter break to help yourself out? If you are taking another class, you might say, Brian, this looks absolutely crazy. Are you kidding me? Data camp. Does anyone see a familiar format to this code right here? Maybe I'll make it even easier. 100 points in the chat if you can identify a familiar format being used right here in this code. You ever see something like that? Anyone ever noticed something like this before? A little coding practice right there? Put the thing before it. You got it right there, Megan. 100 points in the chat. People are saying the tilde dot, all of them. And what is this right here? Well, so finish the whole thing off. So I want to know about this whole thing right here, because I'm sure you've seen this before. I'm sure you've seen this. That's the y variable, right? So this is y tilde dot comma data equals. And then we just have more what's for the function we're running. We just have more what's. Yeah, we're coding a neural net right here. Y tilde x comma data equals another 100 points to Alyssa right there. And then we have more what's, not x's. Well, all the x's are being used with the dot. And then the commas are telling us that there's additional what's for this. Every comma sets forth a new what for this function. Every comma sets forth a new what for the functions. More arguments. Max knows what we're talking about right here. More arguments. Arguments are just new instructions. Great job right there, Nathan. I remember people tell me, like, I don't know how to code. And they're like, Psh, I got this. New arguments. So we have right here a fit control, which is controlling how we fit our model. We have here that we're using model neural net. We're doing a tune grid of the neural net right here. We're doing a preproc, which processes the data to be centered and scaled, which turns it into z-scores. We got the trace equal false, so we don't get this ridiculous amount of output right here. We don't have our trained data. And so if we don't turn off, if we have the trace on, we get all the fun output. Woo! Look at that output right there. We don't need to see that. You turn trace to false, you don't get all that crazy fun output. And now you don't get the output. The line out means linear output. So guess what? And this is such a good connection right here. The line out means linear output. We actually found that out today in class because I put it in as true when it's quantitative. What do you think matters about this if we're doing linear output right here for our neural net? We haven't even talked about neural nets in this class, but what do you think is the point of this line out and the connection to this variable right here? Which if you notice lower on for the activity we did today in the 474 class, line out right here was false, and why? What do you think's the deal? What's the deal with the churn variable here? Why do you think linear output is false? Because what's going on with the churn variable up there? And yes, Nathan, you're seeing it right there because it's a categorical. So we're actually using like the logistic classification methods here. So the only thing that changed about this code was now we're predicting the churn variable down here, and we're going to be doing categorical predictions. So if you look at this model and you want to see how it does, how would we, and we'll turn off the trace on this. You can just put false. How would we evaluate, and this goes to your class, we're doing some review questions right now. How could we evaluate how well this neural net does? Since we're predicting a categorical variable, what could you look at to evaluate this neural net? You could evaluate the what of this neural net on its ability to predict if somebody churns or does not churn. This is where we ended last class. Now, we didn't do neural nets, but this is classification. This is, does somebody leave their cell phone carrier, yes or no? We're predicting yes if they leave. And so what, because that's the level of interest being last. So does somebody leave their cell phone carrier? We'd want to look at the what of this model right here, the what of it. How would we know how well this model does? We'd look at the what of this model. The answer will appear in a moment when the neural net finishes running. What would we look at for this model? Ooh, I will throw some 500 points. Review question from last time. What will we look at for this model right here? We can look at the confusion matrix. I don't know if we can get that for this. I wonder if, will that work? It won't do it. It won't do it. That does not apply here. But the confusion, Nathan, you're on the right track with that. The confusion matrix can be used to compute the what. I'm going to actually bring up the notes right here and show that. Actually, I can probably get a confusion matrix for this. The confusion matrix can be used to do what? Let me try to get a confusion matrix for you right here for this. I want to go and delete everything off here. We don't need a tune grid. Let's go here, close that off. Method GLM. Ooh. So we got the points ready to go. And let's go logistic. We got the fit control up there. There's the logistic. Ooh, it's mad about something. Warnings. We'll take some warnings. Sure. Don't really have much to plot because there's no tuning parameters yet. That's what I thought. Can we get from this the confusion matrix of our model? I don't usually look at it for this. We can. So what's the whole point of this now? The whole point of the confusion matrix right here, and we just ran logistic regression. So it's rank deficient. It's probably about the x's it's mad about. So what's the whole point of this confusion matrix? We're totally back in our class right now. We've jumped out of 474. So you can see the connection between what we do in 474. So what do we need to take from this matrix right now? You should be able to compute it. Compute that metric that matters to get that 500 points right here. Compute that metric that matters. What metric do we need from this? Compute it. And what metric are we looking for in this? What do you think? What metric do we want from this? Oh, I'm on top chat. Well, I haven't seen the answer yet, right? Who has an idea of what we want? We want to know how well this did. How can we tell how well this did? Nathan was on the right track right there. I'm going to throw 100 points for Nathan being on the right track. What is the point of this? Who's got some ideas? We need ideas in the chat. Like, this is what we predict. So we predicted these people would not leave their cell phone carrier. We predicted these people would not leave their cell phone carrier also. So who did we get right? We predicted these people would leave their cell phone carrier and they did not. We predicted these people would leave their cell phone carrier and they did leave their cell phone carrier. We should probably get the same sort of model. I'm going to write our model here. You can see the similarities. We'll go log 2, GLM, and we're going to take the same code we have here, y tilde x comma data equals. I'm not going to click the data set. Oh, I didn't lose it, did I? I need some ideas. Who knows for the big 500 points? Who knows? Losing my place. Really? Here we are. What are we doing? Well, not chi-squared, because that, if you're thinking about the chi-squared, that's the drop 1. How are we going to tell how well this does? How can we examine? Good guess right there, Walker. How can we guess how well this does? I wonder if it comes to the same result. I'm looking at this. This is our way of doing it. There's the log 2. Model does. And 5 to 4. Yeah, it comes to the same result. I thought it would. Using the same methodology. How can we tell how well our model does? Which same code was run up here. Ah, we can't use R squared. Nathan, right job right there. And Megan's on the right track. We can't use R squared. In categorical, we can't use R squared. So Megan says, find the percent we got right. Just do the correct prediction. Exactly, Megan. So what is that going to be called? And who can find that? That's the big 500 points. Megan said right there, find the percent of time we are correct. So what is that called? We got the 500 points loaded and ready to go. We just need to look at the output and be like, okay, we're predicting whether or not someone leaves their cell phone carrier. What percent of the time are we correct? And so what is that called and what is that value? This is like test questions. Like, I know we put questions like this directly on the test and say, find the this of this, which you should know, okay, I need to look at this and find the blank for it. You can't see the output? Can you not see the... Not RMSE. Oh, that's all right, Nathan. We won't be using RMSE because RMSE is typical miss the model makes, and the Y would need to be quantitative to do RMSE. Good guess right there, Cole. The R would need to be quantitative to do RMSE. I like that we're talking this over because these are the small changes to your world we need to know. No more RMSE, no more R squared. RMSE, R squared are done because Y is what? Please say it in the chat. There's no more RMSE. There's no more R squared because Y is what? There's no more RMSE. Kevin sees it right there, 100 points. And Nathan's finding out the what. Nathan, I just need that word for what that is, and you got it. Get those points. Tell me Nathan just computed the what of this model. Nathan just computed the what of this model. He took how many we got correct here and how many we got correct here and looked at the total. Not quite the probability, but think about how well it does, what the model is. So I want you to think of the word. I can tell you the word. I said it last time. That's why I'm making sure people say it today. Boom. 500 points in the chat. Everyone gives some cheers to Nathan and Megan and everyone working this out right here. Everyone working it out. Even the wrong answer. The accuracy of the model. Like, does that make sense? Or sometimes we call it the classification rate. Like how well it classifies things or how accurately it classifies. Sometimes we call the other one the misclassification or, you might say how inaccurate it is. I usually just say misclassification. So the classification of a model or the accuracy would be across here, how well it classifies. Does that make sense right there? So watch this. What's on the Y scale? Accuracy. And here's what's really cool about data mining. This is what I want to show you. Can anyone tell how many models I made, how many neural nets I made? And let's look at the accuracy. This is the neural net I made. Let's compare the accuracy of the logistic to it. The accuracy of the logistic is oh, what do you notice about the accuracy of the logistic to the neural net? I'm sorry, neural net. What do you notice about the accuracy of the logistic to the neural net? That's interesting. What do you notice about the accuracy of the logistic to the neural net? So you can kind of see the neural net. We can actually find the best neural net from this. So if we go to neural nets, we have our neural net stored, and let's go to best tune. No. Best tune is this one. And let's go to neural nets and go inside of it and go to the best tune. Go to models. Just go into models. Oh, final model. No. Results. There we go. Wait, what? Oh, we want the row number of this. It's row number 8. Let's just do that. There we go. What's a neural net? A neural net is based on perceptrons, which are the basis of it. Don't worry, we won't do a whole lecture on it today. It won't be on the final. But the big thing I'm looking at right here is I'm comparing the 2 what's of these models. I'm looking at the 2 what's of these models. The 2 accuracies. And interestingly enough, neural nets, which is a very complex topic, we still have the notes up from earlier today where we talked about perceptrons and how it relates to just regular old regression. So you can just see some side notes on what we talked about in 474. That linear regression is kind of the basis of perceptrons with inputs and all this good stuff right here. We went through and did some advanced examples where we're just talking about coefficients in models. We're not doing this lecture here, but does it feel like everything we do in these classes now looks connected? Where even in 474, what you'll be doing there with coefficients in models and then using neural nets, which we won't do this by hand. We have to know what goes on in the background, but all of this will be done right here for you with this code. You'll create all these neural nets. We actually just created, I think, around 20 neural nets. 1, 2, 3, 4, 5, 15 neural nets. We created 15 different neural nets. And funny enough, you know what's interesting? You'd be better to just make a what right now. We created 15 neural nets to compete with one logistic. And what won out again, everyone? 15 neural nets. The logistic won. But here's what's so cool. What's amazing is we could easily change this from GLM to RPart. And we can make a tree model. And now, guess what? If we look at the tree-based model, we can see how our tree model did, and there's the accuracy on the tree model. So what's winning right now? There's a tree model. We just made a bunch of partition models to see if the partition model worked. You know what's still winning? I just switched to a different model, so now I made a tree model. Still the logistic, still the GLM. I don't know if the random forest, it might ask me for the tune grid. Oh, it's doing it. Well, we'll look at the tree right here. So now I'm making a random forest. There's the code for the random forest. So what do you think about especially this code right here with the train function? This is taking a moment. And this is data mining. We're creating all different sorts of models, which we haven't discussed what these things are. But every single one of these models... Oh, no, sorry, Daniel. Great to have you back. Every single one of these models will be compared on their what. And this is what's most important to your class. Every single one of these things I'm creating right here, which the random forest is taking quite some more time. This is a bunch of trees working together, which should beat out our singular tree. All of these models will be compared on what of each other. Every single model we make right here is going to be compared on their what's. You won't need to know how to do the train. You need to know this. When you're predicting a categorical Y, you will compare your models on their what, or you'll want to look at how the what of the model. This is the big important thing. The accuracy. So this is kind of a peek into the future if you take 474. Also, I hope this, do you feel scared about that code up there where we're just writing train, y tilde dot, comma, data equals, the tr control, fit control, that's cross-validation. We haven't talked about that here in this class. But I'm just changing the method. It looks so similar, right? Method controls what model we are making. So no longer do we have like a GLM or LM. You could put GLM right here for generalized linear model. It's neural net, and I guess I'll show this. Ooh, we can look at our tree in a second here. This is the power of data mining because, and this is the last thing I'll show, and then we'll get real serious right here. This is how many options you have. How many options does it look like you have? Like, let's go find our neural net. Here's the neural net. How many options are there for different types of models you can make? Remember we said GLM? Well, there's a lot of GLM stuff. GLM boost. There's the regular old GLM. We have GLM net, GLM H2O net, neural nets, just a whole bunch of neural net type stuff. What about tree-based models? There's AdaBoost. Black Boost, BST Boost. Should be BTS boost, if you ask me. Boosted trees, well, boost tree, of course. I don't even know what a C4.5 like trees are. But these are all the different things you can do. And we, in 474, we talk about what are tuning parameters and all these different things. But I want to point one last thing out right here before we go look at the last output. What do you think this is about? It says this is for classification and regression. Regression is when the Y is what? And this goes to our class. Regression is when the Y is what? If we're talking about regression, we probably mean this. Like you can say logistic regression, but generally when someone says regression, they're talking about this. And this is, you have to know this when we talk about this. Quantitative. And then classification is when we're talking about like logistic, when we're talking about accuracy. Does that make sense? When they say regression right here, they're talking about quantitative Y values. When they say classification, they're informing you this can be used for categorical Ys. So this model right here, this C5.0, can only what? It is only meant to be used on what? If you read this right here, you could use this right here for what? And we could actually just give it a shot. We'll do this as the last thing because we're doing that. That can only be used for a categorical Y because it says classification. So it really boils down to the basics we're doing right here in our class. So we'll look at the tree right here. There we go. mtry, that's how many parameters it tries per each. I have no idea what this even is. It might work, it might not. Let's say random model. We haven't beat out logistic. Install the package. Well, of course, let's install a package. Why not? So I have no idea what this C5.0 is. Oh, using some Tizbol. So this is a method I've never used before. We're trying to beat an accuracy of 80.7. Random model being used right here. Will it work? Will it not work? Something crazy happened. A bunch of warning message. We didn't crash. And we get a best tune from this because it's got tuning parameters, it looks like. Don't worry about tuning parameters. Let's go to the best tune. There it is right there, model 11. So let's go to the results of this. Random model. And let's go to where's our model? Oh my gosh. Final model, we don't look at that. Best tune, results, model info, model type. We should be able to go to results. So it's results. And we said it was model 11. Random model. Random model. Model 11. Oh! How's it all work? Yes, it does. Yep. It has a lot of that stuff. DataCamp has so much stuff. And guess what? Close. But what's the answer? It actually didn't beat out the neural nets. And there's, yeah, so pretty interestingly enough, logistic, the thing you have learned here today, all this super advanced stuff Brian was doing, this code right here, that code actually beats out all these advanced models. Sometimes the answer is simple. Sometimes it's not. There's probably a better answer. We'd have to spend time to find it, but all models are wrong. Some are useful. Awesome. So what does it mean if our test beats the neural net? Just that's better model. Just that. And then neural net doesn't have any good interpretability. So the logistic is probably simpler. I mean, we can wow people being like, oh, we did a neural net, but our logistic was the best model. And that's kind of the point of this, is to like, what would you love to see? Just the last thing right here I want to mention on this, because this really relates to our class. What do you want to see when you're building these models? What do you want to see? Really high what? And that's all we're looking for when we're doing this. We're just finding out the this every time we build a model. The whole point of this is to look at this every time and be like, okay. Which we can see it for this, for the neural net. I can get you those values if you want, but that's higher than all those. And that's high accuracy, exactly. And so you're trying to accurately predict whether someone leaves their cell phone carrier, and we're just trying different models. So it really just comes down to what's the best accuracy. We're just trying to look at different ways of doing this. And what's so cool about this, you should have an idea of what these do. You don't usually just go and grab one like I'm doing this here. But if we go down here, deep boosted. Okay. Boosted is a very good way of doing things. Boosted trees are about some of the strongest methods we have. It's going to use the default tuning grid. Yep, let's install more packages. This is our last attempt right here at it. Boosted trees are pretty powerful, and this could take a moment. So this is the essence of data mining. I can explain to you about boosted trees. It's basically trees that learn from trees. You see how it's building all these different trees right here? It's like it's building a tree multiple times, and it's learning from it every time it builds that tree. And then it starts over and it builds another tree, and it learns from that tree, and it starts another tree and builds over and builds another tree. It's just building trees continuously and saying, new tree, build a new tree, build another one, build another one, build another one. Keep building that tree, keep learning how to build that tree, keep learning, keep learning, keep learning, keep learning. It's absolutely insane. This is what we have with modern analytics. This. Now, if I put trace equals false, you wouldn't get to see all this nonsense. But you see, it just keeps building a tree over and over again, trying to rebuild the tree. Might have to return to this one because boosted trees is not a quick algorithm. But boosted trees are trees that learn from trees. So you keep rebuilding a tree. It's like you build a tree and then you chop it down. You say, let me rebuild that tree. And then you iteratively keep rebuilding your trees. It's so cool. Anyways, any last thoughts on this? If you can't tell, I love this kind of stuff. I love that we can do this. And I've never done the deep boost. I've done the gradient boosted. What is a tree in the context? This goes back to a tree is what we call a partition model. And have you ever seen this? Who remembers this from Stat 201? Have you ever seen something like this? This is a tree, and I accidentally put major in there. Let's go remove that. That's an identifier. The algorithms in R are a lot smarter than the algorithms in jump. So this right here, yep, good old jump. And so when you think about this, and actually jump even has, I think, ways to do things like boosteds. If you go down here to the panel, which a lot of people don't even realize there's options, but jump has ways of doing boosted. If you go down here to the bottom, decision tree, and there's a boosted tree right here. So the boosted tree actually has parameters you have to enter into it. So here's the parameters. So jump does have a lot of these algorithms for doing that. And these are boosted trees right here, which have like a learning rate, how much they learn from each tree. Overfitting penalties for regularization. Splits in the tree is your interaction depth. And these are things you wouldn't know, but we teach you in 474, like what is the interaction depth? Number of layers, the thing is how many times it grows a tree, which you're seeing are going through this process right here with the iterations. Awesome. We'll return to this. Boosted trees is not a quick algorithm. I was ready for that one. If boosted trees can't beat our accuracy, then it's like, wow, logistic really won out. And sometimes the simple models are the best. Like, you're shocked sometimes that something so simple like just regular old regression works. So, yep. And we can do a lot of these in Jump, but Jump is, a program that is written for you, but your code can go beyond that. That's why we use code to do things, is because Jump is limited by what people wrote for Jump, unless you want to write SAS code, which you can interject your SAS code into it. Let's talk a little bit about building models. Kind of a good transition right here. And this is the last set of notes for the test right here, talking about some model building. So when we talk about building a model, what are we talking about right here? What do you think it means to build a model? It means to choose your whats for your model. Like, model building means we're choosing our whats. Who knows for 100 points in the chat? Model building means we're focusing on building our... What are we building? What are we grabbing? We're going to build our model, and our model needs what? Well, we'll choose the arguments when we write the code. But the important thing here is choosing those X's, right? Well, we don't choose the Y. I mean, I guess we pick which Y we're predicting. But the X's are going to be selected for the model. And then what does every X need in front of it? Or next to it, I guess. No, I'll be in front of it. What do the X's have in front of them, which are going to be important too? What do the X's have in front of them? Starts with a C. We choose the X's, and then the X's have coefficients, which are just like weights to them. We actually saw this with the neural nets too when we were taking a glance at those, but you would have here like an estimate of the true coefficient for the first X. So the idea is we need to figure out what the X's are, what the coefficients are, and then last but not least, you've been doing this for your assignment, you need to what all those coefficients. So here's your goals. Literally your goals are, we'll see this in the slides coming up soon, to figure out what X's there are, to figure out what coefficients there are, And then what do you do with the coefficients next? You got to figure out what x's to put in your model, what coefficients to give them, and then what do you do with those coefficients once you have them in the model? You should probably do what to the person who's reading your report? You should be able to what those coefficients. Big thing for the test. A lot of points on this portion of it that we focus on when we do descriptive modeling. Not combine them, explain. Right there. Don't worry, Daniel and Max. Not simplified, but or you might be thinking about the implicit lines, Megan. You're probably thinking about implicit lines, like when you solve out an equation. But if we're going to kind of talk to someone about our model, we would say, oh, here's my x's in the model. It's got these coefficients, but these coefficients tell me this information about how the relationship with the x and the y variables are. And this whole point right here is we've just been talking about descriptive modeling. Descriptive modeling is what we focus on in 320, and that's the big point of like describing what's going on with the x's. What do you think 474 focuses in on here with data mining? How's that? We're still going. We're still going. If you were wondering, yes, the algorithm's still running. Like I said, it takes a while. What do you think 474 focuses in on? I don't think you can convince me to do that. What do you think 474 focuses in on? 474 probably focuses in on this. Probably focusing in on this for 474. Thoughts on 320? We do a lot of descriptive modeling here, talking about how, what is the impact of like this variable in the model. And then 474 is going to focus in on what for you. Very big emphasis on this in 474. 474 predicting the future, basically. 474 is going to focus in on predictive modeling, predicting the future of data. And then I think it's 471 talks about the action we take. When you think about a prescription right here, prescriptive modeling is going to be the action we take as a company. Because if we can describe what's going on, that's descriptive. If we can predict what will happen, that's predictive. And then if we give an action, we're prescribing someone does something. Does that make sense? So you have here kind of the three key pillars of analytics is describe what's going on, predict the future, and then prescribe an action. Does that make sense? Just follow it in that order. What is currently happening? I'll describe that to you. What will happen in the future? I'll predict that for you. What should we do? I'll prescribe that action. So these are the pillars of kind of what we do in analytics and how we can use our models to either describe what's going on, predict what's going to happen, or to prescribe an action based on the data. And so you see right here, here's the three tasks. What is task number one? Just tell me 3 words. Only tell me task 1 in 3 words. When you're making your model, what? We were reviewing this earlier. Tell me task 1. I could do it in 2 words, I think. Only in 2 words or 3 words, tell me task 1. What are the x's? I like that. So what x's? What x's? Does that make sense, Josh? Great answer right there, 100 points. What are the x's? Like what variables should be in this model? Does that make sense? What variables? Those are the x's. Does that make sense? And like you could go more in depth and be like, should they have transformations? Should they have interactions? Find me the x's. I can do the next task in 2 words. Can you do the next task in 2 words? So what is the next task right here? I want the next task in basically 2 words. So give me the next task right here in 2 words. I've got it underlined and highlighted. Find coefficients. We were talking about this earlier. So task 1 is get those x's. Task 2 is give them coefficients, like weights, like what is the correct weights for those coefficients, like values, just give them numbers. And then task 3 concerns with the coefficients again. What do you think you're going to do with those coefficients after you find them? So task 3 is to do what? Once we find the x's, task 1, give them coefficients, task 2, we're then going to what those to the reader. And it's descriptive modeling, so you could use that word. Interpret. I was going to use interpret. But if you see the word describe, it's descriptive modeling. So connect this right here. The whole end goal is to describe what's going on. And think about this. You have to have the x's, which need coefficients, to describe the coefficients to the reader. So you say, okay, what are my x's? They need coefficients. I'm going to then describe these coefficients to the reader and explain to them 2 individuals who are otherwise identical, but different, blah, 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 blah. You get where I'm going with that. So once again, we want to have the data be a reasonable reflection of reality. And what code would we run? 100-point question right here. What code would we run to check to see if our data is a reasonable reflection of reality? To see if our data, it says right here, we have to have it be a reasonable reflection of reality. That's what that basically says, as in we need to kind of gives it away right here. What code would we run to see if we should be doing this? Like our models should reflect reality and not have like big issues like some bends in the model or heteroscedasticity or non-normal residuals. What am I talking about? Which code right here do we use to do that? This is good review. Like I say, a lot of this class is review at this point. Check regression, Justin knows right there, the check regression. So the check regression, and we will look at the p-values, Josh, you are correct. We will look at the p-values in the check regression, and the check regression is just used to see if our model is a reasonable reflection of reality. Does that make sense? I hope some dots are getting connected because a lot of this is review right now. But when we want to see, should our model be used, we're checking the regression to check to see if it should be used, checking assumptions. Like it should just be called check regression assumptions. That might help with remembering what it does. But the check regression is going to let us know, should we use our model? So when we have this right here, we're trying to find which model is the closest to the truth. Now, this is mind-blowing. I still, even to this day, like, I don't know. There's things in statistics that I'm like, really? Because we're going to talk about some really cool people right here in a moment who definitely know these things way better than I do. Unfortunately, one of them passed about 7-8 years ago. I'm talking about Dr. Akaike. But these people figured out a way to estimate how close our model is to the truth. Now, what's really good to think about this is if you think about the truth, if we had the true if we knew the truth, what would our R squared be? This is probably the easiest thing to think about. If we knew the truth, what would our R squared be? Probably, and you'll see this in the code here in a moment, or the equations. It'd be 1. If we knew the truth and we knew everything, we'd have an R squared of 1. So you'll see this in the equations coming up here in a moment. And you have to get into some pretty, Dr. Akaike has a paper on this, explaining why he does his criteria the way he does, the Akaike information criteria. Akaike, that's how you say it. And we'll talk more about the truth in a moment right here. So you know what's really great? We talked about the 3 criteria for descriptive modeling. Find the x's, give them coefficients, find how, describe the coefficients. Predictive modeling is a lot easier. Oh, I don't have my coin near me. When it comes to predictive modeling, let's do this right here. Let's do, it finished. Let's go over into R. And let's predict if you're going to pass the class. Let's go here to prediction. Let's take a look at that model here in a moment. And the prediction will equal sample from yes, no, and let's go here to prob. Who wants to be an adventurous soul and tell me, prob equals concatenate. Who wants to be an adventurous soul and say, Brian, I'd like my prediction. Brian, we're only doing it for one person. This is, will you pass the class? I will give you a prediction. I will see the future. Max, the answer is, wait, I didn't do it. Sample. Wait. Max, the prediction for Max is, whoo! There we go. Should put a size on this. That'd probably work better. Nathan, do you want me to predict for you? We do this too much, we're gonna get scared. Okay, you ready? Nathan. Woo! Anyone else? Last calls. It's got a 99% probability of being yes. It's got a 1% probability of being no. Megan. Here we go, Megan. You ready? Woo! Will you pass your finance exam? What probabilities do you want here, Walker? Do you want us to? I can run with this current model. You go, Walker. You ready? Finance exam for Walker. The answer is yes. The crystal ball says yes right there. If you run this enough times, you will get a no eventually. What we could do, we can make our code a little bit better and put the prediction on here. Lindsay says, there you go. Look, Lindsay right there. There you go, Lindsay. If we run this code enough times, we will see a no eventually. You saying, Brian, it's not happening? Well, you just got to speed run it. Speed run. Oh, I can't This button does not. Oh, there it is. Well, as long as you're of age. I'll give it a 50-50, to be honest. Okay, here we go. Here's the real deal. Real deal right here. Will Walker pass his finance? Walker, this is not a binding contract right here, but will Walker pass his finance? The answer is... Woo! I'll take it. Take it right there. Some positivity, 100 points in the chat. What do you think is the only thing that matters in a predictive modeling? What do you think is the only thing that matters in a predictive model right here? What do you think is the only thing that matters? This is the only thing that matters. So positive today. We love it. The only thing that matters in a predictive model is what? It's the only thing that matters. Everything else, rock? It doesn't matter. This is the only thing. And how it works on new data. So you're trying to predict the future, right? So the only thing Walker's going to care about right there is if that prediction is right in the future. Does that make sense? Walker's going to say, Brian made a prediction, and he's going to see if it worked on the future. So you know what's really interesting about the equation? When you look at descriptive modeling, we'll worry about this here in a second. Don't worry about the model hierarchy stuff. If you look at descriptive modeling is over here. If you look at predictive modeling, and that's why predictive modeling is a little bit easier to kind of grasp. Predictive modeling only focuses in on the what variable. It only cares about this. The only thing predictive modeling cares about is the what variable. When you think about predictive modeling, it's just the what variable. Don't worry about the model hierarchy stuff. Oh, no, there's only two because there were two values. In the... I can drop that code for you real quick if you want. Or ask me on the Discord. I'll talk about it. It only cares about the y, right? Predictive modeling only cares about the y, but descriptive modeling only cares about the x. And we got here some good review. Here, I'll drop that code in the chat real quick for you, Walker. Not Walker, Nathan. Right there, there's the code for you right there if you want to run it. And we'll take a look at our boosted tree at the end here. I'm excited. I hope that boosted tree did better. Model hierarchy means what? This is a good review right here. Now, model hierarchy, do we have to conform? Do we have to have model hierarchy? Do we have to have model hierarchy, yes or no? Is it like, oh my gosh, you have to have model hierarchy. If you don't have it, you're absolutely crazy. No, you don't have to. You know, it's a good idea. It's a good idea. We like to have it. It says model hierarchy is often, though not always, respected, so we try to have it. If we have an interaction, explain to me. If we have an interaction between x1 and x2, what do we need to have in the model? If there is an x1, x2 interaction. I agree with Nathan right there. Nathan, good answer right there. I'd say you probably should have a justification why not to. You technically don't need a justification, but I'd prefer you to have one. It'd probably be good statistics to say, here's the reason why we didn't carry model hierarchy. I'd agree with that sentiment right there, that I think you should use a justification for not having it, but you don't. Someone will be like, I just don't like it. Well, there you go. So why is model hierarchy not carried through right there with the x1, x2 interaction? We have an x1, x2 interaction, and there's not model hierarchy there because why? Yes. So the way I think of this one, good question right there, is if you have an x1, x2 interaction, to carry model hierarchy, you must have what in your model? The way it works with interactions is if there's an interaction between the x1, x2 variable, which we see right there highlighted, you must have what in your model? This is how model hierarchy applies. It's basically the idea of you must have the lower order components. So x1, x2 interaction is built from what, and you must have those in your model to preserve model hierarchy. Think of it as like building a house up. What should we have to have model hierarchy, which this one does have model hierarchy, this one does not. We must have the, great job, Walk right there, 100 points. We must have the x1 and x2, and this is where we preserve model hierarchy. So these down here, these ones that are no, do not have x1, x2. Like this one has x1 but does not have x2. This one has x2 but does not have x1. So exactly Walker said, so perfectly separately, not in an interaction. Here we have model hierarchy preserved because in these two examples, we have either indicators, and now what are we missing right here? You can see it. We're missing the ambidextrous. Why? You're welcome, Joshua. Joshua, 100 points. Thank you for asking that. You know what, Joshua, you get another 500 points of the day. We are going crazy on points these days. But Joshua asked a question that he didn't know, and I really appreciate that. Always ask those questions, even if you're like, wait, what? Because I bet you someone else was like, can you explain that model hierarchy again? So in these two examples here where model hierarchy is preserved, we have here left, right, and ambidextrous. Now, why is ambidextrous not being seen right here? Why is ambidextrous not seen? A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S. Yeah, okay. They're in order. Why is ambidextrous not seen in alphabetical when we do categorical X's? So where do you think, let me ask you this. When we don't preserve model hierarchy, good theory question, where do you think R goes if we don't, like if we remove R, where do you think where do you think right-handed would go right here? If you don't see right-handed in this model, where has right-handed gone? Now we have to make predictions for right-handed people. We have to make someone's right-handed. We got to make a prediction somehow. Well, think of this. They're not left-handed. Kind of answers the question, right? So what has happened to the right-handed people right here? Where are they now? What team are they on? So we don't have a right. We can't say they are right-handed. We just say, are they left-handed or not left-handed? Kind of answers the question. Where have the right-handed gone when we remove model hierarchy by not carrying it? Kind of. I think Joss has got it right there. So they're going to the reference level. Does that make sense? So this extra slash right-handed. Does that make sense? Since right-handed's been removed, we don't have an indicator for right-handed. So now someone is either left-handed or not left-handed, and we've removed the model hierarchy by not including all the indicators. So it's very important to know this. If you don't include all the indicators, then, oh, no worries. 100 points, Megan, right there. Does this make sense? If you don't include all the indicators, where does an indicator go that is not included? If you don't include all the indicators, an indicator that is not included would go to the where. Like for this example right here, an indicator that is not included would then go to the what? It would go to the reference level. And by not including all the indicators, you have violated what? By not including all the indicators, which you can do it if you really want, but it's one of those things like, why are you not making a thing for right-handed people? Yeah, I don't want to. Okay, well, that's reasons. You've violated model hierarchy. Does that make sense? So this would destroy the model hierarchy by not including all the indicators for categoricals with 3+ levels, because they'll create 2+ indicators. So violate. Yes, this is stat ethics right here. So once again, when you leave out an indicator, this is going over the same notes we see right here. If you notice right here, we have removed summer, and summer now goes to the reference level. So now you have it's either spring, winter, or it's fall/summer. Does that make sense? There is a fall and summer level for it's either fall. I hate to say or, but that's all observations that are either fall and summer. Like, but you're not fall and summer. It's just that was it fall, was it summer? That's the reference level. And then the other observations are spring and winter. Does this make sense? What happens when a indicator is removed? If you remove out an indicator, it goes to the reference level. What you would do then is you would just indicate, is it spring? Is it winter? And if the answer to both of those is no, then it'd be the reference line, and the reference line is all data that's fall and summer. So does that make sense, Nathan? Whatever we get for this reference line, which would be the black line, the parameter estimates for the reference line would be based on all data that is fall and summer. So that one line right there, we'd get 3 lines from this, and that reference line would have parameter estimates from the data for fall and summer. So it would be the same prediction. It doesn't matter. It wouldn't matter if it's fall or summer, because it would not be spring, it would not be winter. And it would all be predictions from that line. So that'd be the reference line with its own intercept and slope and all that good stuff. Got the sniffles today. Does that make sense right there? So fall and summer are just one line right now. They've combined forces together. And we wouldn't care if it's fall or summer. Yeah, so like so it would get the same. So fall and summer have the same implicit equation right here. Does that make sense? And you would get this by going right here and putting in zeros for spring and for winter. It would just be the reference line. So does that make sense, Nathan? Like when you write out your equation, the reference line would be fall and summer. So you would just put in zeros for season fall, season spring, season winter. You'd put in zeros. Does that make sense? And then whatever the reference line is would be the fall summer line. There's not a fall and summer line. There's just the fall summer line. There's one line right there. You won't solve for two lines. Since we don't have, I could try to write it out. Good question right there, Nathan. Thank you so much. 100 points. Since there's no equations on this slide, I don't have a good way to solve it. And maybe that's where the disconnect is. But I could try to do that right here. This is just like examples. I think the polynomial is probably the easiest one. And do message me on Discord on it, and I'll maybe try to walk through some more examples. With the polynomial, if we have something right here to the third degree, what must we have for like in x4 to the third degree? Are we doing whichever one we're doing? Whichever x to the third degree, like if it's x sub, let's go 2, that's the one we're using. If we have x sub 2 to the third degree, what must we have? If you have x sub 2 to the third degree, to preserve model hierarchy, you must have what? Which that one does not preserve model hierarchy. So think of this one as a tower. So if you have x sub 2 to the third degree, you then must have what to preserve model hierarchy? You're right, Joshua, you're right. Keep going, though. Keep going. You must have x sub 2 to the second. But you don't have a base of the tower yet. So you have to have it to the second, but you must also have it. And great job, Joshua. They're right there. Great job. You must also have x sub 2. Does that make sense? You have to have all the powers that go into it to preserve model hierarchy. So this is generally a good idea. Generally. You can remove the intercept. I'm not a huge fan of that. So you're supposed to include the intercept. Here's what it looks like if you remove the intercept. I still don't know why someone would do that. In my view, it just sets the intercept to 0. So I'm not a big fan of this one. It's just a way of understanding it conceptually. Like the easiest test questions to write are something like we show you an equation like this, and we ask you, does this equation preserve model hierarchy? And the answer being yes or no. So that's probably one of the easiest test questions. We think about, if you think of us as instructors being like, let's write a test question, we'd say, is model hierarchy preserved here? And why on this one is model hierarchy not preserved? And we'll kind of draw it out over here on the side. Why for this one is model hierarchy not preserved? So the answer would be no if we asked it. So why would it not be preserved? There's no x, exactly. This term is missing right here. And so you don't have the x2 to the second power, and thus we do not have model hierarchy. Exactly. Does that make sense, Josh? And so you don't have to draw it out, but it can make sense if you look at it and say, okay, we're missing the x2 to the second power, so we don't have the model hierarchy being preserved right here for this. Great job, Walker, right there. Excellent, everybody. Following along. Great job. And so the intercept, if you remove it, you remove model hierarchy. Yep. It's a bad idea. I agree. I think it's a bad idea. Once again, all models are wrong. Some are useful. I had a student get mad. I put this on a test. I was like, George Box once said this about models, which informs us that we'll probably never find the right model, but we could, find a model that works. And they're like, they wrote something in the side like, why do I need to learn quotes? Here's why we need to learn quotes. Because when I was watching the 2016 election, so 2016 election, Trump versus Hillary, all the pundits, if you remember, everyone, oh man, it's 5 years ago now, so I got to watch as I get older. I'll be like, 2016 election, and someone will be like, I wasn't born then. And I'll be like, you weren't born in 2016? They'll be like, Brian, you're a 70-year-old man. I'm 18. But no, I'm sure people remember 2016 now. Every prediction seemed to be off for Hillary by about 4 or 5 points. So what does that mean? That is the what of these models. If you think about it in our statistical terms, if we have a model predicting how much Hillary will get for a certain thing, And then all the predictions are off right here by about 4 or 5 points. She was lower, so the actual points are going to be here. That is the what of this model. Not quite standard error. It's just the miss of the model. Not typical miss of the model. Because we're not talking about like Brian did a whole bunch of misses and looked at it. Brian would just watch and then they'd be like, Hillary should get this, and then she'd get this right here. I'm just looking at one of those. Just looking at one of those. So it's like, she should get this. Boom, right there. Kevin got it. Residual. It's just a residual. So what does that mean? Well, that means I should just take my whole model and shift it downward. Does that make sense? If every prediction seems to be off by about 4 points, well, you just take the model, you just shift it down like this. So that means if Hillary is expected to win in a landslide in some place, it might be close. And if it's going to be close, if they predicted it was going to be close in some area, what does that maybe mean right there? If they said it'll be close in this area, so if Hillary was supposed to win in a landslide, it might be closer than we thought. If it's close, that might actually mean what? They say it's going to be close, but Hillary's going to win. Then we might actually project her to lose. Everything gets shifted down because I'm noticing this constant shift. It's like if I told you this. I have a clock at my place right now that is exactly 12 hours off. I'm talking to the millisecond. How great is this clock that I have that is as off can be? It's exactly 12 hours off, and I'm talking like nanoseconds here. Like it's as perfectly wrong as wrong could be. How good is that clock? It is the most wrong clock that exists in this world. No clock could be more wrong than it because it's 12 hours off. It says PM all the time when it's AM, and it says AM when it's PM. How wrong is that clock? And I'm talking like the atomic clock wishes it could be this good. How wrong is that clock? Who knows? Because this is the important thing of this quote. The clock I have, Colt's answer about the arm. Well, it wouldn't be RMC. So the clock I have is how wrong. It is 12 hours off. 12 hours is the most you could be off. If I'm like, is it 1 a.m. right now? You'd be like, Brian, that's super wrong. How useful would it be, Josh? How useful would it be to have a clock that is perfectly on time, but says AM versus PM? I think I can look outside right now and see that it's bright out and be like, it's probably the afternoon. It's probably not 1 a.m. The thing that, Megan, you're kind of right. It'd be so useful because I just have to flip the AM PM. But if I do anything to this clock, it'll totally mess it up. I can't change it. It'll totally mess it up. But oh no, that's sorry, Cole. That's all right. I was like, that's no worries, Cole. 100 points, Cole. Does that make sense, Megan? The clock is as wrong as it could be. It is perfectly 12 hours off. But all I have to do is look outside and know that it's the afternoon and be like, wow, it's 1:08. This clock is perfect. It's my time. So when you think about it, models can be wrong but still be useful. Does that make sense? Add a sticky note, exactly. So does that make sense how a model could be very wrong? And we know all models are wrong. We're never going to get it right with statistics. We don't even know what the truth is. More on that soon. We don't know what the truth is, but we can use our models in some way sometimes. That's our goal, is to find a useful model that'll help us make predictions. Very important quote from George Box, and that's why we need to understand it like, yeah, it's wrong, but we can still use it. Nothing's ever going to be perfect in statistics. You kidding me? So what are our goals again? Review slide. 1, find those X's. So many words to just say, what are your X's? 2, find those coefficients, the estimates, the coefficients right here. And last but not least, interpret. Goal 1, goal 2, and goal 3. Find the X's, find the coefficients, interpret said coefficients. And our goal right here is to find our model that's closest to the truth, which is so weird to think about. So let's take a look at some random models right here. Now, this model right here, if you look at it, is being created from this X. So we are predicting this Y from these X's, from this X, excuse me. These other X's are completely and utterly what? Say that word, you know what's about to happen. These other X's are completely and utterly what X's. So we have an XY relationship, and then we have a bunch of what other X's. What's that R stand for before uniform? It's going to generate 50 x's whatly from a uniform distribution. Those are random x's right there. So what model would you bet on? Would you want to use the model that uses just the XY relationship? Or would you want to use the model that uses all of them? Would you want to use the model that uses the XY relationship, or would you want to use the model that uses all of them? Which model would be better? Which model sounds like a better one? Our norm is random normal. So it generates random normal. Great question right there, Nathan. Our norm generates random normal numbers. So the R stands for the random and the norm stands from the distribution it's drawing from, like R uniform. So the R uniform draws random uniform numbers, where the R norm generates random normal numbers. Like a normal looking distribution randomly takes numbers from that, or a uniform distribution randomly takes numbers from that. Good question, Nathan. So you would, well, think about this. What is the relationship right here? This model is built off this X, right? So these other random X's are kind of what? If you think about the other random X's, they're kind of garbage. They're nonsense. They don't have a relationship with the R norm right there. Yeah, that's noise. Actually, great question, Nathan. That's noise added on, lest we would get a perfect model every time. So this is random disturbances on the model. So it's like, there it is, says a disturbance right there. So it's like random variation, so we don't get a perfect relationship. So then it's actually got a little bit of confusion because there's error on the model. So we want to use the model that we actually are building from, and we only have this X. We don't want to include these other X's. So how would we know this? Well, one thing you'll notice is that when we estimate the coefficient of X, you actually have more uncertainty. So maybe I'll highlight with the other color. You actually have more uncertainty when you add in the extra variables. This is a bad thing. We're trying to understand the X variable, and the other X's are kind of just in there bouncing around. We're like, no. The truth, which if we knew it, is that the one X makes the model. I can see the truth, which we normally can't see. This is the truth, that there is a one X in this model. That is the truth. But these other X's are now going to clog up this model and confuse me. We don't want that. How could we figure out what the truth is? So our goal is to find the truth right there, and our first model is a lot closer. Second model is very far off. Well, these two gentlemen, which you'll probably never hear again after this slide, Callback and Leibler, came up with this idea of measuring how close our model is to the truth. Callback and Leibler. You'll never hear them again after this. But you will hear about Dr. Akeyike. Dr. Akeyike, and let's go take a look. Famous Japanese statistician and mentor to Dr. Humphreys Bosdigan of our department. Oh my gosh, where'd it go? Sure, let's go back here. And, oh, not even on the main screen. And let's go to Hirotogo Akeyike. What? Where is he? Here he is. Here's the gentleman himself, Dr. Akeyike. He actually came to UT quite a few times, and like I said, he passed, unfortunately. 81, good, and just very, very famous Japanese statistician right here. And his paper, and they even dedicated on Google, but if you look at how many times his paper has been cited, it's absolutely insane. And a lot of times people cite his paper on the information criteria. It's got 17,000 citations. That is absolutely insane. Here's the number of citations on his papers. Is at 29,000, 51,000 citations. Holy mac! He's got Bayesian stuff. Of course, he's got Bayesian stuff. That's Dr. Humphreys' big stuff. If your paper is cited, and a lot of times people don't even cite it, which is kind of sad, but 17,000 citations as of 5 years ago. 5 years ago, it had 17,000. Now it has 51,000. If your paper is cited 51,000 times, did you write a very important paper? By web, oh, those different things, by Google Scholar. If your paper is cited 51,000 times, how are you doing? It's pretty insane. It's pretty insane. His lesser papers are cited 961 times. That's pretty just, yeah, pretty important right here. Pretty big research. And that's not even updated as of, let's go Google Scholar this real quick because I want to know. Ake Google Scholar. Oh, can we not? Google Scholar. Oh, here it is right here. Well, this is the actual paper I think we're going to. A new look. Is it not showing? It should show the temporarily unavailable. No. H-A-K-E-K. Have they changed the way this works? That is not him, I think. Well. Look at another time. Absolutely amazing stuff right here by Dr. Ake. And let's go back to the notes right here. So when we look at this right here, it looks really complicated. But I want you to see this. What is that? Everything here looks pretty complicated, but that's the important component right here. What is that, and what does it relate to? What is SSE? We have to know what SSE is. What is SSE? Who knows what SSE is? All these great questions that build to our knowledge and help us understand. What is the SSE of a model? We were kind of talking about this earlier because it is based on residuals. And it's what we do to the residuals. More importantly, the residuals are the error. Then we will do something to the residuals. What will we do to those residuals? And then what will we do to the squaring of those residuals? The SSE is basically a quantity of error. It's like how much error is there in our model? Because we don't want to think of these things just as mass. We're going to sum, great job, Kevin, right there. We're going to sum the squared errors. Like visually, we always want to think about visually, what are we doing? If we have, do I have that drawing still? Oh, it's on previous slides. When you think about sums of squared error, the sums of the squared error is when we literally take our error here and we square it, and then we sum all the squared error. Does that make sense, Kevin? You take the error, you square it, and you sum all of it, because you have to square it so it can be positive. This model is a bit ridiculous, but we want to sum the squared error. So by summing the squared error, we can get a metric of how bad our model is. What is the smallest possible summed squared error? The smallest possible summed squared error is what? Very important to conceptually understand this. 0. Check this out. See the equation? We're taking the log of it. So if you have no error in your model has no error. Guess what you get? Your Ake information criteria for a perfect model with no error would be negative infinity. So what do you want Ake information criteria to be? You want your Ake information criteria to be very, very, very what? Because the best is negative infinity. So the best, a perfect model would have an Ake information criteria of negative infinity. So you want it to be low. You want it to be small, because the bigger error you have, like if you have an error of something like, let's say like 5 right here, you're going to get a positive number. If you have decimals, it actually goes into negative numbers. So negative is fine. It just means you have decimal sums of squared error. Does that make sense to everybody right here? Like conceptually, you don't want this to be big because it's going to make the log of it bigger. And then let's look at the last component. What do you notice happens here when you add predictors, which are the Ks in the model? By adding predictors, the more X's you add in, which are predictors, your Ake information criteria will now do what? Sample size, of course, will kind of help it. But the predictors is a key component that if you add more predictors, more X's, what happens to your Ake information criteria? It will do what? Because you're adding them. It's just how many predictors there are. That can't be a negative number. So adding predictors would do what to the Ake-Ike information criteria? Great note to have. Mathematically, we can see it. The Ake-Ike information criteria will go, if we add predictors, what will it do? The Ake-Ike information criteria will do what if we add more X's into the model? By adding more X's into the model, the Ake-Ike criteria will get bigger. Exactly. The Ake-Ike information criteria will get bigger, which means we're further away from the truth. Like, how do we know what the truth is? Well, it's an estimate of how close we are to the truth. The more negative it is, the lower it is, the better. The closer we are to the truth, the higher it is, the further we are away. So when you look at this right here, we've actually got a more complex way of doing it with the Ake-Ike information criteria corrected. And so with this right here, take a look. You've got all of this right here, showing you the Ake-Ike information criteria for all of these different models right here. Or not for all these different models, for a penalty term right here, because I'm going to show you something next to end class. You've got a penalty term right here, and then you've got an additional penalty term. This is penalty term 1, and then this is penalty term 2. What do you think these models try to do? The models try to select much simpler or much bigger models. What do you think with these penalty terms, which are based on the variables you pick, which are added onto the model based on the variables you pick? These models will often try to, or this criteria will often try to select on what models? Not bigger, because bigger will hurt it. Unless the bigger model does really good, then it'll overcome the penalty. So we penalize ourselves for adding variables. So oftentimes you'll get simpler models. Does that make sense? These are added on. Remember, we want this to be very small. This is basically what we have right here. And then this is penalty term 1. This is penalty term 2. Original Ake-Ike information criteria only has the one penalty term. And here's how we use it. I want to show you it in practice to end class. So don't leave, whatever you do. How do we use the Ake-Ike information criteria? I have the perfect example, and it is used like this so much. We did a competition in 475. It was tons of fun. So I'm going to get this video loaded up right here. We did this last class. Someone said best class this semester, and that really made my day when someone said that in the chat, last class. So here is last class for 475, and I'm writing their models out right here. Let's go check it out. Here is 475's last class. And what do you think I'm doing right here? I'm making all their different models right here. So here's what the groups had for their different models. We're coding out the different models. And then what do you think I'm looking at? Well, we're looking at, we did RMSEs. No, we should have done AIC. Well, that can be it too. Did I look at AICs of the model? Dang it, I should have looked it up. We can look at AIC or RMSE. Well, just tell me right here. Which groups are groups 1 from this code right here? Which groups are groups 1 in your opinion to end class right here? Which groups or groups 1? We could have done AIC also. Did I run AIC on this at one point? I know we've done AIC. In which groups are groups 1 and why? Can you look at this code right now and tell me, with your knowledge from this class, for 475, which groups would win and why? Or group. Might be a group. It's not. Which groups would win and why? 1 minute on the clock. Can you tell me from your knowledge right now, which groups would win and why? That is correct right there, Kevin. Why? You're correct, 100 points. Why, Kevin? You are very correct. Why? You know what we're going to do? We're going to let one last thing. Kevin's right because they have the lowest RMSE. But I know we did ARIMA with AIC. And I'm going to end off showing this right here. I want to show some AICs to end. Okay, let's go take a look at this. Last question of the day right here, another 100 points. Who wins right here? Does our model win or does the ARIMA win right there? Which model wins in this? Last question of the day right here. Does our model win or does the ARIMA win and why? Can you look at this output and tell me which of these wins and why? We've got our model that we created right here and we've got the ARIMA. Which wins and why? Careful, it's negative. You got it. I think actually it tricked me too. I was like, yes. Oh, it's negative. I know, right? 100 points. That's in a class. The AIC, and there's the AICC, and there's the BIC, which is the Bayesian information criteria. Does it make sense what you're seeing here, Kevin? You're seeing the AKE information criteria for these different models. Also, the corrected version of the AKE information criteria. We don't use the Bayesian information criteria, but it's the same sort of idea. So all of these work off the same metric, that lower is better. So your model can be selected right here, and if we're going for the model, we would actually use that ARIMA 210011. So the ARIMA 210011, which are the parameters for the ARIMA. You're not learning ARIMA right now, don't worry. The only thing to care about right here is lower AIC is better, and we can look at this and know the answer that the ARIMA right there is the model we would pick. Thank you, everybody. Went 1 minute over, but just wanted you to see this in practice. This is how you use it. You just get the output and you say which is the lowest AIC? What's the lowest RMSE? So we got to see 2 examples today where we looked at the RMSE and the AUC. Now, AIC, excuse me, AIC. I said AUC. More on AUC in other classes. Do you use AIC on our upcoming assignment? I think. Let me double check right here. Let's go take a look. Let's go take a look. 320. I cannot believe it's the last full week of class. We have right here the last, we will not be using AIC. I think the last assignment, AIC. Okay, here's information. There's AUC, AIC, ROC, so many terms, MAP, MASC, so many terms. We're finishing off with logistic right here. And then I don't think we'll do, because we're not going to try to overload everything. The instructors are talking in the background right now about what will be done and where we'll stop. Yeah, Dr. Panel's syncing stuff right here. Should be good to go. I added 2 days until the 24th. Okay, so we'll be doing an activity, and I'll be putting out a video for that. Good stuff right there. Awesome stuff. Can you explain that model hierarchy equation? Yes. So let me try and let's go take a look at I want to see how the crazy model we made worked or didn't work. Do we call it neural net? Where's that? Oh, deep boost. Here's the deep boost. Whoa. Okay, it's not as much as I thought, but still. Oh, man, it didn't. All that work? You gotta be kidding me. Really? 77. All that work and logistic beat it out. All that work with that model we ran that took forever, and logistic won. Well, what do you know? Try all the super advanced stuff you want to try that takes forever to run, or you could just run a logistic. But you never know. Every model's different. Never get the same results. So what we're going to try to do right here, we're going to try to write out a model. Let's do this right here with the ambidextrous right-handed. That was the tree thing. Yep, the tree thing did not beat out the logistic. What you've learned in this class right now is the best model we have, and a simpler one. So Nathan, that's exactly it. The crazy tree thing that I did that made all that output, it still is beat out by the regular old logistic with not much going on. So the very simple model, which is probably better to use in a lot of instances when you can, yeah. I'm going to try, I don't usually try to destroy this model hierarchy. Okay, I didn't do data equals. There we go. Okay. I don't usually destroy the model hierarchy with the left-right. So let me try to remove it. I don't know if this will work. Nope, doesn't like it. I know one way of doing it. I could recode the variables. Remove indicator. Here we go, someone's asking. Well, they're saying a minus, like I'm doing, but that's no. The person got 0 upvotes. That's the wrong answer. little chill music right here while we try to figure this out, and then I can show it. So I could recode. Person gives such a weird answer to that one. This is good. Someone put out a good video on this. I can do it the way... So I can do it the way I'm thinking of, Nathan, right here. So what we're actually doing, like, just trying to... I want to find the answer to it. But what you could do is you could go right here and go to survey $10 handedness 2, and you could do if else survey 10 handedness is percent in percent contained in the vector, and let's go right or ambidextrous. I can't spell ambidextrous. If it's contained in the vector right / ambidextrous, you could go right here. Let's do that. Run the following code. Oh, maybe just gonna look better if I do this. Run the code. I'm gonna go factor on this. I wish there was a simpler code to do this. So now run the code A/B, and if not, left. Okay. So now what I've done is I've created a factor, and now handedness 2 would actually be a better way of looking at it. Or I could overwrite my handedness, and now you just see handedness left. Does this make sense right here, Nathan? So this is what it's essentially doing. If you remove out something, which I'm trying to think how to remove it out. I don't usually do it. I don't usually break the model hierarchy on a indicator. So now the reference line, like if we looked at this, if we visualize this model right here, the visualization of the model is going to be, and you see the coefficient's so tiny you can barely see it. There's a left, or ambidextrous. I put B. An ambidextrous right line and a left line, and the ambidextrous right is the reference line. So that is the reference line right there, and the left line is this right here. I think the coffee got to me. I might need to eat some lunch. I don't know. Office hours are a little slow this morning. I'm feeling a little out of it. No. Oh. I might take a quick break right here and relax up. So might be like, you know what? Take a break real quick. But hopefully that makes sense right here, how we're combining it. So what's the implicit equation? Good question right there. He'll finish off with that. So you have two implicit equations now. So A/R equation. We'd have here, we're predicting someone's height equals to the intercept plus this times weight. And then the implicit equation for the left is going to be this added to the intercept. Does this make sense right here, Nathan? That we would simply add to the intercept this, and there's the new intercept, which you can see that the red line has a higher intercept. So the left, so there's only two lines now because the reference line is the A/R line, and we have here the equation. You can see it's like 50, it doesn't go down to it, but 56.6 or so. I want to look at one last thing right here. It will probably work, but I wish it would. It doesn't work with it. Gotcha. There's a library I got today, which I've been trying to do more. ggplotify, and you can take as ggplot and put something in here like the visualized model might work, and it doesn't like it. It says nope, won't run it on it. But it did run the effects test. I think it's not creating it though. It doesn't like the visualized model. Oh, it does. It does. It's just not doing something. So now we could actually go here and go like plus GG title and say hello. And no, don't we got a hello on here? So I don't know if it is doing it. That's interesting. Yeah, it looks like it's not liking it so much. The visualized model is its own kind of thing. What I might want to look at, visualize regression model with Plotly. Oh, Python. Why Python? What Python? No Python. In R. No Python. Poly regression right here. Ooh. That's so complicated. It's so much extra work. Someone seriously didn't write a code for this. It looks nice, but top answer. Well, there's their fit. Going Plotly, add markers, and the fit. Okay. Google, what you doing, man? We'll see if we can get a good plotter here to end. So they're piping through their data. So we need to pipe through the survey 10. They're calling Plotly. Their X and their OX equals. So, we can't do the multiple regression on this. It's going to get mad. So we have to do like height and weight. And they call it fit. So let's call it fit. That's the X. That's the Y. That's the X. Yeah, I mean, it looks nice. Looks nice. I don't know. I mean, it's more work, and I don't know why someone hasn't just turned this into a function, because maybe a lot more work. I guess you pipe through your data, because you go here and go fun equals, I like doing this kind of stuff. And put that inside of here, and let's say data, and we'll call this xvar, xvar, yvar. Oh, and then we need a fitted. A little more work. We'd have to fit our model inside of here. Well, let's do it real quick. Let's do it. Yvar, there's the y fitted. So we need our fit for our model. Fit for the model being created. And so this is yvar, xvar, data equals data. And so let's go here, yvar, comma, xvar, comma, data. And let's call this ggplot. And so we should be able to go to ggplot or ggplot regression. ggplot regress. And let's go to the MT cars dataset and do HP. And let's go to, or let's predict the miles per gallon from the weight of a car and the MT cars dataset. Does it work? Doesn't like it. WT not found. MT cars. Last little thing right here. WT not found? What? Well, wait, Y tilde X. Let's do that. Doesn't like it. Weight not found. Data equals data. And data equals data. Still saying not found. Well, we'll take a look at this function later. Ryan, trying to get my function to work. It's saying nope. Well, might take a break right now. Just feeling a little, I don't know. I love coding. I want to solve problems. We'll take a look. We'll be back later. Bye for now, everyone. Bye.